Okay, greetings, Bob Pettit. We're looking at module 3, which is the metabolic determinants of fatigue and recovery, part 2. The slow component is not what its name is cracked up to be. So let me reveal the provocative title. The slow component is actually associated with the use of fast twitch fibers. So in and of itself, you're kind of like, whoa, why did they call it the slow component? So we'll explain that. Um, this paper here, Burnley and Jones, they're both British. I'm not sure where Burnley has migrated to. I know Andy Jones has been at Exeter University for, well, I think his whole career, and he's quite an interesting guy. He's I think done a lot for the field and really hasn't been recognized for it. And then there, I really struggled to find a paper with Jens Bangsbo. Uh, Anybody who uses Homer Simpson in their slides is an A+ in my book. He's a really interesting dude. I'm not. I think he's Scandinavian. He shows up in blue jeans with a sports coat when he gives a talk, or sometimes you'll see him wear a leather jacket. A, a, a fascinating individual, very thinking way outside the box, and his contribution is really looking at ions and at that level for fatigue. So I thought it might be good curveball to throw one of his papers in there. I can't find the ideal paper. I've always walked away from his lectures thinking, my goodness, wow. And then I can never find a article that he's written where it's just summarizing, hey, what do I know? And I wish I could, because he's a fascinating person. So that's our topic for this week. Let me go ahead and turn the slides on. And so we begin the topic with this idea of oxygen deficit. It originated with A.V. Hill. You saw a photograph of him earlier, and he believed that this deficit was repaid subsequent to the exercise. And so anything, here's the volume of oxygen, and then this is the commencement of exercise. So we're about a little less than half a liter at rest, and then the oxygen uptake can rise, and then we achieve this steady state, and then all of the energy prior to that wasn't met with the aerobic metabolism was incurred by anaerobic energy systems. And wouldn't it be neat if we could quantify that green sliver and measure that and find out, well, what about a maximum measure of that? And so those protocols evolved, not without their problems. So this was the traditional view. Whatever this gray band here was, it's same graph you just saw. It's now gray instead of green. It was believed that the same curve over here filled the same geometric space. And so there was this belief that the deficit and debt, the debt was repaying the deficit. And we know from George Brooks and several other people that that's not a true picture of what's really happening. The rapid portion of the debt was considered what people would call the alactic acid, or the replenishment of phosphagen, and then the slow portion of the debt was considered the lactacid, or replenishment of glycogen from lactate. And we know there's, you don't have, you have a finite amount, and you need to eat food to replace the glycogen stores. So albeit lactate can replace some of those glycogen stores. They won't be replaced to their full measure. And so this idea came along of, can we measure this finite capacity of glycogenolysis? So break this down to lysis, and that is slicing down glycogen. So it's a little bit from glycolysis, which is the generic term for using glucose and breaking down glucose. Glycogenolysis refers to taking glycogen and either using it aerobically or using it via lactate. And so this is the fast glycolysis when we go from glycogen to lactate, and the slow glycolysis to Krebs. But we know that the amount of glycogen stored in the exercising muscles is limited. So if I were to ask you to do a task that was rigorous and it involved more muscle, like, for example, treadmill running, well, because you're involving more muscle, the amount of energy that you can derive from glycogen, either in fast or slow glycolysis, is larger than the amount you would get from, say, cycling. So this is what we're being specific to the when we say anaerobic capacity, we're being specific to the task. But if we can measure to the task, and we're saying we want to predict how well you will perform cycling on a track versus in the lab, that's what we're trying to capture with these measures. And so along came this technique called the maximally accumulated oxygen deficit, or MAOD, and it involved exhaustive exercise. You needed to deplete all of the glycogen stored in the muscles used for that task. And how it worked would be you would subtract the aerobic contribution to the bout, and then you would know, well, whatever was remaining was coming from anaerobic energy metabolism. And so, in theory, it takes approximately 2 minutes to exhaust the anaerobic capacity. And I've actually heard the basis for the test that I do is that it takes a little longer, about 150 seconds or 2.5 minutes. And so usually this equates to about 110% of the power that you tap out on for a VO2 max. And we've kind of hit on the importance of custom protocols. So if, this power at VO2 max is somewhat nebulous, because if I do one protocol that's very intense, and I finish the protocol at 8 minutes versus a protocol where I can go to 14 minutes, let's say, well, the power outputs at the end of those tests will be different. The power outputs for the shorter duration tests will be much larger than the power outputs for the longer tests. And the same holds true for the treadmill. So that is one hole in one problem with this MAOD method. There are a few others. And then the last thing to mention is that you use multiple oxygen demands at lower intensities to extrapolate with linear regression the sub or supramaximal demand. And so this is a figure from that article that you kind of dove into for the last module, which is myself and Ida Clark wrote it. And if you look at figure 1 of that, there's these dots in the figure, and then there's some black dots representing 105 and 110% of the power. So I'm going to provide you a spreadsheet that runs through that. And so here's, and I do this to show you the simple of how simple this is to do. So if I take, I've got these power up, it's already recorded, and I've got the corresponding auction responses or auction uptake that's associated with each of those. So I've got 1.8, 2.1, 2.5, 2.9, and then 3.8, and that's where they tapped out in their max test. And so then what you do is you say, well, let's go ahead and calculate 105% of this value, the W peak. And so I'll do that 315. And then if I just, some people are not savvy with Excel, so I'll just show you some tips. If you use the dollar signs, now when I drag that down, it automatically populates and it keeps the blue cell constant with the dollar signs. See the column and the row. So that's kind of a neat little trick. So this is 110%. And what we're doing is we're going to say, well, we want to ask that individual to come in and ride at those intensities, which we know exceed the power that evoke VO2 max. So if I type in into my equation here the slope, and it's asking me the known y's, which is the VO2. I'm going to drag and highlight those. And then comma, it's asking for the known x's, which is the power. I'm going to drag those in here. And you see this value. It looks same as value up here. And then I'm going to go ahead and do the same for intercept. So I'm going to enter the y's, and enter the x's. And so you see that on the plot here. So if I simply did the same with the actual graphing of the data, so this is a plot of that same data, and I'm going to right click. I'm going to say, all right, add a trend line, linear, and then I want it to show the equation. And voila. So you see where those functions are coming from. And then what I'm going to do is I'm going to say, well, I want to predict these black dots here. So I'm going to do regression. Remember y equals mx plus b from whatever math class that was in. So the y is the VO2. The m is this value here. I'm going to plug that in times x, which is my known wattage, plus my b, right? So, and then I want to lock in those two variables. I'll do that real quick here for you. And I'm going to drag that down. All right, bam. So I've got 4, and I've got 4.2, and the units for those are liters per minute. You can see now what I'm going to ask that subject to do is ride at 315 watts. Now I know that it's impossible for them to achieve 4-liter VO2 response because their VO2 max is 3.8. The demand energetically would be 4. So if theoretically they were fitter and they could do a GXT and end at 315 watts, their VO2 max would be 4, but they're not able to do that. So what we're doing is forcing them to work at capacities exceeding the aerobic limits. And so if I look at these two graphics over here, we see that the 315 watts versus 320 watts. Well, for 315 watts, they can go for 3 minutes. If I add just simply 15 more watts, that person now can only go for 2 minutes. And this is real. Like, I've seen it be as minimal as 5 watts, 7 watts for certain people. There's that real finite tipping point, and when you encroach that tipping point metabolically, it makes a huge difference. And I'll show you that curve in a moment. But you can see now how they calculate the maximally accumulated oxygen deficit, or MAOD, is shown in the math of this example. And so what you would do is you would use a metabolic analyzer, and you would say, all right, how much VO2 was consumed in minute 1? How much VO2 was consumed between minute 1 and minute 2, and then minute 2 and minute 3? And you would do the same for over here. And then what you would do is you would accumulate the total amount of oxygen consumed. And so when you do that and you subtract the oxygen demand, so the demand for a 3-minute bout would be 4 times 3, or 12 liters. And so you see here 315 is 12 liters. And then for 2 minutes at 330 watts, it's 8.4 liters. And then we say, well, how much you accumulated in that span relative to the demand. So there's a deficit that you can quantify. And it turns out in this example, the deficit is the same, an MAOD of I think it was 1.7 liters. It's been a while since I looked at this. Now, before I X out, this is fantasy land. You'll never get the same subject doing this performance and getting the identical measure. So there's some inherent variability to this measure. And it's not due to the oxygen response. I can tell you that. Because if I max test you now and 3 days later, your VO2 max doesn't change that much. But this little area, this little sliver, that either green or gray box that we were looking at, this guy fluctuates. I'm not going to save. So there you have that. And the article explains it in a little more detail if you're looking for more guidance. Remember, recollect from the last module that the threshold, as we're exercising and we surpass the lactate threshold, oxygen uptake is still occurring. So we're gonna have continual use of glucose and glycogen in the Krebs cycle. The Krebs cycle continues to run, but we reach a point where it's not enough. The conveyor belt's not keeping up, and we need a faster supply of ATP. And so we use the lactate system. And we use either the glucose coming in from the blood or the glycogen that's stored within the muscle. What ends up happening with the oxygen response, and what I'm showing on the right panel here is this is the oxygen response to constant exercise. So let's say this was 160 watts. As long as I'm below the lactate threshold of 173 watts, it evokes that, and you learn how to measure that, or how that's measured. The oxygen response will be a steady state, just as the slide showed earlier. However, at, at intensities exceeding the lactate threshold, you'll see this slow component emerge. And this is above the expected intensity. And I'll explain a little more about that in a minute. But let's first cruise through real quickly what is causing this additional oxygen response, that this slow rise in oxygen. And so there were a lot of purported causes that were investigated. Could it be the lactate? Could it be your intensity is higher? It's we know at higher intensities, epinephrine is secreted at higher levels. Could it be the Q10 effect, muscle tension? This idea that as you rise temperature, you rise metabolism. Ventilation, is it due to we're breathing harder and so therefore the diaphragm's consuming more oxygen? Or the type of muscle that you are utilizing? Well, you know the answer. I've given it already, but it's interesting and worth our time to review. So here's the lactate response. You see this nonlinear rise, and then this is VO2, and we're expecting it to rise here, but there's a departure in the expected response. I've only seen this departure in VO2 response in 3-minute stage protocols. When you do 1-minute stage protocols, you do not see this departure and slow component during incremental exercise. You definitely see it in constant exercise. So what Poole did was, I must have deleted that slide, unfortunately. I'll just summarize it for you. He basically electrically stimulated the calf muscle of dogs, and while they were contracting their muscle, he infused lactate, and he found that there was no effect on the response of oxygen. In humans, they did infusions of lactate and found if you give me lactate, I'll just go ahead and use that preferentially for energy and spare glucose. And then there's some speculation that the gluconeogenesis, the taking of lactate and forming into glucose by the liver, might cause a little rise in oxygen, but that wasn't really stipulated or investigated in these two studies. This is a paper by Gazer, and what he did was, I don't know if I'd want to be in this study, but it was novel. They measured the normal epinephrine responses in people through blood draws that were doing an exercise test, a graded exercise test to exhaustion. And the highest epinephrine level they observed, they recorded that. And then what they did was they said, all right, we're going to have you exercise at an intensity that is exceeding threshold and evoking this slow component. And we're going to infuse that same amount of epinephrine that you had at maximal exercise, but at a submaximal intensity, but rigorous enough to cause this slow component. And as you can see from their data, the lines are directly on top of each other. Another study you probably wouldn't want to be a subject in is this study where they use these hot water pans, and then they stuck an indwelling electrode into the thigh muscle of the person to confirm the temperature in the muscle is elevated. And the idea was, well, if you elevate temperature, you might increase the metabolic Q10 effect. You might promote vasodilation or shift the oxyhemoglobin dissociation curve. In spite of those theoretical effects of increasing temperature, there was no effect on slow component. And so now we get into the effect on ventilation, and you see here, this is a study by David Poole at Kansas State, where they measured the departure of ventilation relative to work rate. This is a percent of VO2 max. You can see there's greater hyperventilation that occurs. No surprise there. And that when they measured the oxygen going into the exercising muscle, and then they took venous draws, and what they could basically do statistically was account for that 86% of the amount of oxygen entering and leaving the muscle, and how much of that was attributed to the slow component was due to the limb, the muscle itself, and then that left about 14% of unexplained, where is this oxygen being consumed. So his theory is that, yes, some of the oxygen is being utilized, some of the slow component is being utilized by the disproportionate increase in oxygen uptake from for the breathing muscles. And finally, the idea of this size principle, we kind of touched on it in the article, the review with myself, Anita Clark, where we see that slow twitch is the first order of recruitment, then the type 2A and the type 2B. Well, we know energetically that the type 2B fibers consume more oxygen per given change in force. So how this relates, if I were to give you just a practical example of what I'm getting at, if I have you run at 2 miles per hour, and I measure your oxygen response, and I measure that same response at 2.5 miles per hour, I would say, well, I expect the oxygen response at 2.5 miles per hour will be a little more than 2 miles per hour. So I might see a gain in VO2 of maybe 1/3 of a liter per minute. And if I do that same metric at, say, 8 miles per hour, I don't know how fit some of you are, but let's assume we're talking about myself. I could run at 8 mile per hour. I would venture to say I'd last about 5 minutes or so. Maybe in my youth I could go longer. But if you went to 8.5 and you measured the oxygen consumption and the net change or delta in the VO2 between 8 and 8.5, it would be like well over a half a liter difference. So even though the change in intensity was the same, the metabolic response was vastly different. And it's due to the fact that you're using inefficient muscle fibers. They're like if you were to compare the Prius versus the Humvee in terms of miles per gallon, you're tapping into muscle fibers that are not efficient. And some EMG studies corroborate these results. However, there was some debate in the 90s and 2000s over it. I think most people agree that the slow component, all said and done, it's this, a little bit of ventilation, mostly 86% due to this here. The slow component is due to the inefficient use of type 2 muscle fiber. Some ventilation. It's not related to temperature. It's not related to epinephrine. It's not related to lactate. And we know that in higher intensities, the gain in the slow component is greater in comparison to lower intensities. And so this led to the introduction of exercise domains. So we have several domains shown. The moderate domain, which is below lactate threshold, and you can go all day long. The heavy domain, which is above lactate threshold, but below this parameter, they're labeling as CP or critical power. Some people will also refer to this as the maximal steady state or maximal lactate steady state, although people are debating whether the mechanisms are the same. I think the arguments boil down to poor measurement, people who are inexperienced with these tests. And I think the same holds true with ventilatory threshold and lactate threshold. If you're good at doing it, you'll find they're the same thing. But you can see the gain is much higher here relative to the expected. So that the heavy domain, this they call the severe domain. Actually, this scale has been renamed. It should be moderate, heavy, severe, and then extreme. I'm sorry I didn't catch that beforehand. This is an old figure. The other error in this figure is that the VO2 is touching VO2 max. So there is a point in exercise where your intensity is so intense that you reach fatigue before you hit VO2 max. And so the lines here that are drawn are the expected line. And then this is the dashed line is the actual line, and the gray is showing the difference. So what is the expected versus actual? So let's pull up the data from the last module. And we said, all right, at 110 watts, we expect that this person exceeded their threshold, the gas exchange threshold. So just to review, that was this, right? So here it is, and then it's going up. Here it is again in VeVO2, 110.5. So if we were to look at an intensity in the moderate domain, that would be an intensity anything at or below 110.5. So if I go to, say, 85 watts, and I pull up and I highlight that, and I look at my expected VO2, because I've used the interpolation method, would be 1.46 liters. And when you put them on a bike, because that's what this was, a bike test, you put them in a bike and you set it at 85 watts and you say, all right, let's wait and see what your oxygen uptake response is. You're going to come darn near close to that 1.46. You can look above and below. You can see, well, it's 1.3, 1.36. It may not get up there. It'll be somewhat in the ballpark. When you look at the intensities of threshold, and then this is the intensity at W peak, 195, that's where they ended their test. If I put them at an intensity above 1.95, they're going to have a huge rise in oxygen uptake that won't reach VO2 max. And that's that extreme domain. Then what you'll read in the Burnley-Jones article is that usually what's called delta 50, halfway between threshold and max, is critical power. That usually ends up being about 80 to 90% of VO2 max, or the power evoking VO2 max. I would argue that it could be lower. Usually it's like 40, but 50 is a rule of thumb. But when you actually evaluate people and do the techniques, it's usually a little lower than that. And so if I were to put the person, say, at 125 or 127 watts, my expected VO2 would be 1.7. Actual VO2 would probably end up being more like 1.8, 1.85. If I put them at an intensity of 140, I'm expecting 1.97. Here's 140. I'm expecting that. Actual VO2 is going to be like more like 2.5 liters. It's not quite. It will be 2.4. And the reason I say that because 2.5 is VO2 max. And as long as you're below critical power, you can achieve that steady state. So let's return to the slides. So that's what that's referring to, is you can have a delayed steady state if you're exercising between threshold and critical power. If I exceed critical power, which a fair assumption is anything above for this subject would be anything over 150 watts. You're gonna have them go, and eventually they're gonna hit 2.5 liters. It's only a matter of time. And the higher you are, the faster that will occur. So wouldn't it be cool if we could actually predict that? Teaser, we can. So that maximal steady state or lactate, when you measure it in blood lactate, and really did a lot of this in Australia last spring, they're not buying into the auction, but still a fun visit, fun experience. You can see the green here, it's rising, but it's not rising above 1. So it might have been like 5.2, and then it's hanging out at like 5.8. And some, if you bump it up to the 290 here, you can see, well, this is rising, started at 6, little over 6, and ended at 8. So they eclipsed the 1 millimole per liter between 10 and 30 minutes. It's an arduous test. You got to sit there for a while. So what this leads up to is an explanation of the critical power concept. And so I've got a picture of the award-winning best actor, Vin Diesel, right? You've seen the movies. Now here, learn the rules. We've got the gas tank. We've already talked about the gas tank, right? The difference between the gas tank and the motor, and the health of your motor. Now we want to talk about the nitrates. So this is the fuel source here that is neck and neck in the race, and then he flips the switch, right? So you don't start the race and flip the switch. You wait. So the idea behind this turbo, or what's called on here the W prime, is it's finite. You don't want to tap into it too early. Otherwise, you're not going to win the race. You want to be strategic about when you use this blue tube. If you tap into it at a higher intensity, so you can see this open circle is just, this is time, this is power output, and this is VO2 response up here. So we see a pattern, a trend. If you go back in your notes and look at TRIMP, take that curve and flip it the other direction, because that's what they were looking at. So, and the irony of that TRIMP curve was they expressed it as a percentage of heart rate. They did it as a percentage of energy systems. Now, take that TRIMP curve, rotate it, and you'll see if you do it relative to this dashed line here, we call this critical power, the gas tank. This is the limits of your aerobic system. So this is around 85% of your VO2 max. If you if you exercise above that limit, then set your watch. The higher you exercise relative to that limit, the faster you will reach fatigue, or in this case, time, the time limit, with which you can sustain exercise. Now, compare that with the metabolic response, and you'll see that at this lower dot here, the VO2, it reaches VO2 max, but it takes a longer time to do it. These middle dots here, you can see the open circles hitting there, the triangles hitting there, and you might ask, well, why is this above VO2 max? Because the original authors didn't use the verification bout. If they used the verification bout, that line would have been spot on those dots. And then finally, this dot over here, the triangles, you can see the VO2 response, bam, it's getting up there much quicker. And so there's a tight relationship between the response of the VO2 slow component toward VO2 max and the use of W prime. And so the traditional way of measuring this was with different time trials of different distances. So I'm going to use the speed for this example. So this is running. They ran 1,000, 1,600, and 3,000 meters, and we recorded the times that they did. And I've got that plotted. Let me